Okay, so we were comparing in the last video how to interpret Ka, Kb values if you're given two or three acids or a couple of bases which seemingly seem to have the same magnitude in their Ka or Kb values, all right? Then you come to the coefficient. So here in this list, nitrous acid has a value which is 4.5 times 10 power negative 4. Hydrogen fluoride is 3.5 times 10 to the negative 4. And then formic acid is 1.8 times 10 to the negative 4. So all of them are in the same ballpark region, 10 to the negative 4, all right? So how do you compare them? You look at their coefficient, okay? So which of them has the largest coefficient? That would be nitrous acid, all right? So it's 4.5 times 10 power negative 4. Therefore, among the three, nitrous acid is got the largest Ka value, so it is the stronger of the three weak acids, all right? The formic acid has got the smallest among the three, therefore it is the weakest among these three acids, okay? Now, if you compare all of this list of weak acids, phosphoric acid is at the top of the list because its Ka value is 7.5 times 10 power negative 3, right? So among the weak acids, phosphoric acid has got the highest Ka value, and therefore it's the acid that dissociates the most among the weak acids, all right? It breaks up the most, okay? Now in the bases, if you look at the numbers, ammonia, you have given methylamine carbonate and ammonia. So among these three, ammonia is the weakest of the three bases listed, and then methylamine with 4.4 times 10 power negative 4 is the strongest among these three, all right? Here in table 11.5, it summarizes how to determine acids and bases and what their characteristics are. If you have a strong acid, that means that Ka value is really large, much greater than 1. That's why it's unidirectional. It forms only products, only ions, 100% dissociation, all right? So the arrow is always pointing towards products. If it is a weak acid, then the Ka value is small. Therefore, the arrow is likely to go in the reverse towards the left side because most of the acid remains unbroken, less than 100% breakup, okay? So a small percent of the acid will break up, okay? As for a strong acid, its conjugate base is going to be weak, okay? And you've seen that. If you have something like HCl, right? The Cl minus is pretty weak as a base. Whereas if you have a weak acid like water, its conjugate base, OH minus, is strong, okay? So it's opposite. Again, if you look at strong bases, same thing, kind of like strong acids, it goes towards completion. Large Kb values, 100% dissociation, its conjugate acid is going to be weak, all right, okay? So if you have something like ammonia, right, if you compare ammonia and water, ammonia is definitely stronger, but the ammonium ion is quite a weak acid, right? So its conjugate acid is weak. A weak base, its equilibrium will position will be directed towards the reactants. That means very little of the base is breaking up. A little bit of it forms the the conjugate acid and so on, but and then its conjugate acid is going to be strong. All right, okay. So when water acts as a base, right, its conjugate acid H3O plus is going to be pretty strong. Okay. All right, so write the acid dissociation constant for HNO2, nitrous acid. Okay, so HNO2 is going to react with water. It's weak, so double arrow, H3O plus and NO2 minus. So products over reactant, all right? Ignore water, water is a liquid. So H3O plus times NO2 minus divided by HNO2. That would be the Ka expression. Okay, 11.5, we are going to be looking specifically at the self-ionization of water. All right, so water, of course, is neutral. It doesn't really ionize at all. Pure water should be just unionized water molecules, but a very, very small, a minuscule amount of water molecules do self-ionize. So one water molecule will donate its proton to the other one, and then that becomes H3O plus. The water molecule that's donated its proton becomes OH minus. All right, so you can see here there are two water molecules. One proton comes off, goes on to the other one, forming the H3O plus, and what's left is the OH minus. Okay, so this is called as the self-ionization of water. When you write the Ka expression for this particular reaction, on the left side it's just two water molecules. You can't include them in the expression, so it's just going to be H3O plus times OH minus. All right, because it's water, instead of Ka we use W, so it's Kw. Okay, right, so one water gives up its proton to the other one, and that leads to an H3O plus formation, and then this is then left with an OH minus. All right, so if it goes in the reverse direction, that H plus will go back to the OH minus because it's pretty strong. All right, and then you get back the water molecules. All right, again this double arrow indicates this is a very weak kind of reaction. As I said, only a few molecules of water will undergo this type of thing. Okay, so when you write the expression, the K expression for this, it's going to be H3O plus times OH minus, right? And then instead of A, you put the subscript W for water, right? So Kw is H3O plus times OH minus. Now, when it's pure water at 25 degrees centigrade, the concentrations of H3O plus and OH minus are 1 times 10 to the negative 7. All right. So when you multiply 1 times 10 to the negative 7 squared, you get 1 times 10 to the negative 14. All right. So just add 7 plus 7. That's how you get this 14. All right. So when you're multiplying something which has a coefficient of 1, and it's basically the same number, you're kind of adding up that coefficients. All right, so you get 1 times 10 to the negative 14, and that's the Kw at 25 degrees centigrade for pure water. Okay, now this is a constant. That number will never change, all right, because it is an equilibrium constant, right? So Kw is always going to be 1 times 10 power negative 14 for water. All right, so again, you're not using any kind of molarity or concentration units, you're just using the numeric value. So if both are equal, then water is neutral, all right? However, if that H3O plus is more, all right, if it is greater than 1 times 10 power negative 7, that means that solution is acidic. However, if the H3O plus is less than 1 times 10 power negative 7, or rather the OH minus is greater, then that solution is basic. Okay? All right, so what happens if you are asked to determine the OH minus given H3O plus? All you have to do is take the Kw and divide it by the given value for H3O plus and you get OH minus. And vice versa. If you're given OH minus and asked to find out H3O plus, you just take the Kw value and then divide it by the OH minus concentration. So pure water is neutral, and as you can see here in this picture, the H3O plus concentration is exactly equal to the OH minus concentration. They're both 1 times 10 power negative 7. However, when you have an acid solution, you can see that the H3O plus concentration is much greater than the OH minus concentration. All right, that means it's going to be greater than 1 times 10 power negative 7. All right, so it could be anywhere between 1 times 10 power negative 1 to 1 times 10 power negative 6. All right, okay, anything greater than 1 times 10 power negative 7. What happens when it's basic? That means the OH minus is dominating. All right, so the H3O plus is less. Okay, so the H3O plus concentration can be anywhere a number less, numeric value less than 1 times 10 power negative 7. So 1 times 10 power negative 8 to 1 times 10 power negative 14. Okay. So acid solution, H3O plus is dominating, base OH minus dominates, neutral, they're both equal. Okay, so you have a neutral solution, they're both equal, 1 times 10 power negative 7, both H3O plus and OH minus. Kw is therefore 1 times 10 power negative 14, the product of the two. Okay. In an acid solution, suppose H3O plus is 1 times 10 power negative 2, okay, then OH minus has to be 1 times 10 power negative 12. As long as the coefficient is 1, you can add the 2 to the 12 and you get 14, all right? So that's how you can do that. Now, if the coefficient is not 1, then of course you have to just plug it in into your calculator, all right? So again, 10 power negative 5, all right? That is greater than 10 power negative 7, all right? So therefore it is acidic, okay? 1 times 10 power negative 8, okay? That's much less than 1 times 10 power negative 7, so it's basic solution. 5 times 10 power negative 11, again, much smaller than 10 power negative 7, so therefore it's basic. All right, so if you're given H3O plus and asked to calculate OH minus, just divide the Kw by H3O plus. If you're given the OH minus and asked to determine H3O plus, divide the Kw by the OH minus, all right? So what is the H3O plus given OH minus, which is 5 times 10 power negative 8, okay? Kw is 1 times 10 power negative 14. Divide this by 5 times 10 power negative 8, and that will be the H3O plus, and that comes out to be 2 times 10 power negative 7, all right? So this is larger than the neutral, so the solution is acidic. All right, we'll stop here.